In this video, we're going to take a look at lists in Prolog, specifically the unification rules for lists. They're in fact quite similar to what we've already seen dealing with compound terms, but now we have to deal with some additional operations of accessing and constructing lists, similar to how we had cons, car, and CDR in Scheme, but a little bit different when we're dealing with Prolog. So to start, a list in Prolog is two square brackets, so the empty list is just two square brackets with nothing between them. If we want a list with one element in there, for example, we could say x equals the list with just the terminal a in there. Or just a regular old list, we could say x equals 1, 2, 3, 4, a list with 4 elements in it, and that's what x now equals. Now, the unification rules for lists are pretty similar to what we've seen before with compound terms. We go element by element through each individual list, first making sure that the arities of the two lists match, and then individually can either term be unified. So, for example, if we had the list 1, 2, 3, that will unify with the list 1, 2, 3. That says both these lists have the same arity, and then element for element, 1 unifies with 1, 2 unifies with 2, and 3 unifies with 3. So that will unify fine. We can also deal with variables in our list, so we can say x, y, z will unify with the list 1, 2, 3. And again, that's true term by term, so arity 3, x unifies with 1, y unifies with 2, and z unifies with 3. So we get the unifier x1, y2, z3. And we could also have compound terms in our list, so we could say something like x, comma, b of y, comma, c of 3, equals a of 1, b of 2, and c of 3. So we just have 3 terms in there that happen to be compound terms. So the top level of the list here has arity 3 in both cases, so that's good. And then element by element, x will unify with a of 1. b of y will unify with b of 2. They have the same functor, same arity 1 here. So y will unify with 2. And then c of 3 and c of 3, they're the same compound term, so they'll end up unifying with each other. So that's true if x is a of 1 and y is 2. So similar rules as we've seen before, just element by element through the list. Now the tricky part dealing with lists is what's known as the pipe operator. The pipe operator works a lot like both cons as well as car and CDR, depending on the context for how we're using it. So a pipe operator will unify with 2 different parts of a list, the head and the rest, or the tail. So as I said, it works kind of like cons, car, and CDR depending on the context. So let's see how it looks in terms of a consing operation. So for example, if I say the list A, that will unify with the list A, pipe the empty list. Which is to say, this list here on the left is a proper list. Just like in Scheme, it doesn't show the empty list at the end of the list, but it is there. So you can think of this as A cons the empty list, and that just is the list A. Right, so if I did that slightly differently, I could say x is A pipe the empty list, and that just gives me the list A. So again, proper lists, and the empty list at the end is not displayed. Now, we can also cons elements into bigger lists. So for example, I could say L equals the list 1 pipe, and then the list 2, 3. So this says construct a list out of the head being 1 and the tail being 2, 3. So what is a list that will unify with the head being 1 and the tail being the list 2, 3? Well, that's the list 1, 2, 3. So if we want to read this forwards, or in terms of a cons, we can say cons 1 to the list 2, 3, which, as we know, just adds the item to the front of a list. And we can create long-form lists if we want. We say x equals 1 pipe the list 2 pipe the list 3 pipe empty list. Close 3, 2, 1, and close. So this is essentially saying cons 1 to cons 2 to cons 3 empty list. And that, again, gives us a list as we're familiar seeing these things in Scheme. So lists in Prolog do work similarly to in Scheme, but the syntax is obviously different. Now, it's worth pointing out that these two lists are different. So A pipe B, equals A comma B. So on the right here, A comma B, this is a proper list. It's as though we had used the symbol format from Scheme just to say apostrophe A, B, and just made a list out of those symbols. On the right here, we're saying cons A to B. So it says join these two things together. So these are not the same. If I say x equals A pipe B, we just get x is a pipe b. It's just essentially it's like a pair of those two elements. So it's no longer a proper list in this case. Whereas if we use just the normal format of putting commas between everything, that creates a proper list with that empty list at the end. Whereas this one we can see does not have that. All right, and let's do one other combination here. So x equals a pipe, bracket, b pipe, empty list, close, and close, pipe, bracket, c pipe, d pipe, empty list. Close d, close c. Should be 4 of these, I think. Close and close. I think so. So I recommend pausing the video at this point. Try to figure out what this is going to create. What is the value of x in this case? Okay, and now let's run it and see. And now we have a comma b. So on this side here, we have just a proper list. From here. That gives us a proper list. That's cons A to cons B to the empty list. And we have a similar construct over here where we're saying cons C to cons D to the empty list as well. Now what we've done is we've made that a list item and piped them together. So the entire thing is a proper list where we have cons A, AB, and then CD as a second term, and then an empty list hidden at the end there. So a proper list. This extra set of brackets here means the tail is a list, so we can create a proper list out of this. Okay, so the pipe operator can be used to sort of cons things together, depending on how we're constructing these things, but it can also be used to char and CDR things apart. So as I said, the pipe operator will unify with 2 parts of a list. So if we have a full list, like 1, 2, 3, 4, 5, if we unify that with something that's using the pipe operator, it's going to separate the 2 parts of this list, the head and the tail. So the head being the first part and the tail being everything else. So if I said h pipe t here, this is going to unify with this list in such a way that h gets the head value and t gets everything else. So if I full stop and run, h gets the head, the first item, and tail gets everything else. Okay. Important to note here that the head is always going to be an atom, assuming we're dealing with a flat list, and the tail is always going to be a list. Whether that's a full list or the empty list, either way is true. Okay, so tail variables can be matched to empty lists. So if I said, for example, h pipe t unifies with the list that just has a in it, well then there's an element for h, so the head of this list is the element a, or the term a, and the tail of this list is everything that comes after a, which is that empty list. So a list with 1 item can still unify with this form. It's a very common form to have h pipe t to join or split lists apart. But this form does assume that there's at least 1 element, so if I use h pipe t equals empty list, that can't unify. So there's no value for head in this case. The tail could still be the empty list, I suppose, but there's no value for both of them, so we can't unify this form. So h pipe t assumes there's going to be at least 1 element in our list. All right, let's do a couple more practice things here. So let's do 1, 2, 3, 4 unifies with underscore underscore pipe x. So again, I recommend pausing these videos, take a look at them, see what you expect this result to be, so what the unifier would be in this case, if it will unify at all, and then I'll walk through the answers. All right, so in this case, we have to unify this list on the right with the list on the left here. So this form here says there's at least 2 elements, so underscore comma underscore. We don't care what those 2 elements are. And then pipe would be everything else. So instead of just being 1 atom, we're going to take 2 atoms off the front of the list. And then x will be everything after those first 2 items. So that will be 3 and 4 in this case. So we get the list 3, 4. Similarly, if I said underscore 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 pipe x, we get x is the list 4. So notice it didn't just take the element 4, it took everything after the first 3 elements, which happens to be the remaining list, which is just a single element. But it gave us that single element inside a list, because that's how this pattern gets matched. Okay. Now if we wanted that to not be in a list, we could say 1, 2, 3, 4 equals underscore 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 comma x. And now because this is exactly 4 elements long, the first 3 elements, these don't care variables, will unify with 1, 2, and 3 and not be bound because we don't care. And the last one, x here, will unify with the 4th element, and we should get 4. Now that only works if we have exactly 4 elements in our list. If, for example, we had comma 5 here, then that just won't unify. There's no way to fit 5 numbers into 4 variables. All right. One other way we could get rid of the list from this example, so we could say 1, 2, 3, 4 unifies with underscore 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 pipe x. But instead of just saying x, if we want to just get the element out of that, we could wrap that in brackets as well. And that says unify this entire structure with this list on the left. So this entire structure says there needs to be 3 elements, 1, 2, and 3, and then the rest needs to be a list with exactly 1 element in it. Okay, and in that case we get a list that has exactly the element 4. Now again, this won't work if we have more than 4 elements. Just put a 5 there. That becomes false. The reason being the rest doesn't match this form. The rest isn't a list with a single element in it. Okay. Now if we had not put those brackets and we just said x there, then it doesn't matter how many elements, as we've already seen. Oops, gone way too far. 1, 2, 3, 4, 5, 6. Underscore 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 says get rid of the first 3, and then pipe x says take everything else, so unify with the remaining list. All right, so there's lots of other things we can do with these lists. Let's take a look at a short practice problem. So in the uploaded code you should find a file called, that's not the right one, what is the right one? Sorry for the tabbing, called studentstructure.pl. So I'm just going to open this here as well as in Notepad++. There it is. Okay, so here's the student structure. It's a lot like the employee database that we had, so it's just a bunch of facts in a pre-specified format. So for example, each student here has an ID, has a name, and a list of grades. So the name is a compound term that has a single element or a single term as its arity, and just that term is a 2-element list. Okay, so it's last comma first inside a list. And similarly with grades, we have 1 term inside the grade construct that has just a list that in that case then has 4 elements. Now we're going to ask a bunch of queries about this. Let's do a simple query to start here. So let's get both these on the screen. There we go. So for example, we could ask who is student 1001? It's not in the list here, but if we want to know who is student 1001, we provide all of the pattern that we know. So it's going to be student. We know its ID is 1001. We don't know their name, but we know the structure of that is something like this. So what we could do is just say name X. We'll just do that. We don't care about their grades for this one, so we can just leave a don't care variable. So 1001 will unify with 1001. It won't unify with any of these other atoms. Any of these other numbers. Name, the functor will unify, and then the arity here is 1, and we've provided 1 variable. So that 1 variable will unify with the 1 term inside this compound term. In this case, x will unify with the list Allerton Alice. And then this don't care variable will unify with this entire term here and throw it away. So we run that, and we get Allerton Alice. So that's one way of doing it. Now, if we want to be a little bit more specific, we want to get their last and first name separately, we could provide the structure. So in this case, it's a list structure that has exactly 2 elements, and we'll provide variables for each element. So last, comma, first. In that case, now it says the exact same answer, but now in a different structure. We get the individual values rather than just a list of values. Okay. Similarly, we could ask what are student 1001's grades. So we'd say student again. We know it's ID 1001. We don't care about their name in this case, but we do care about their grades. So we could say grades as a term here and get the entire list. Or if we wanted, we could actually just say grades. Right, and that will unify with the entire term. We can see grades is all that. Or if we wanted, we could go into that, use the lowercase g, and match the individual item. So now this functor, lowercase g, is a constant. Grades will unify with this constant grades. Arity 1, so then the term x will unify with this list of values. Okay. So let's get to these queries now. So how did Alice do on assignment 1? So this assumes that there's only one student named Alice, or I guess for every student named Alice we'll get this information. So to do that query, we do something like student. We don't know their ID anymore, because it could be any Alice. We do know the name is Alice, so it's name. We don't know the last name, so we're going to have to provide information right in place. So we'll have to provide the list, and a don't care variable for the last name, and then the first name, the constant Alice. Okay. So name Alice, and then we want to know how they did on assignment 1. So similarly, we have to provide all of the structural information so that the pattern matching, or the unification, will match the constant, in this case 92, with some variable. So we have to create all the brackets and the commas, all these brackets and commas, so that the pattern matching will unify our variable with that specific term. So we put in grades, the brackets. Now this is in a list, so that's there. And we only need the first element out of the list. So we can actually use the pipe operator here to our advantage. We can say A1, and then pipe everything else we don't care. Okay, so pipe says unify this structure, this square bracket structure here, with some list that has at least one term and doesn't care about everything else. So it has a rest, so it's a proper list is pretty much all we're guaranteeing here, that has at least one element. And in this case, we want that first element called A1. I missed a bracket somewhere, yes? I don't see it, but let's just walk through it again. Student name, there it goes. I forgot to close the entire student bracket. So we had an open bracket out here, and I forgot to close that one, so there it is. Okay, so student unifies with the functor student, arity3. We don't care about the ID. We do care about the name because we have that information, so that unifies with the functor name, with a list that has a list with two elements. So then the first element we don't care about because we don't know the last name. The second element we do care about because it's Alice, so Alice unifies with Alice. And then it goes through and says, okay, unify the grades as we just saw, where the first element unifies with A1 and the rest unifies with the don't care variable. All right, so let's copy this one into our answers. There you go. All right, so how did Alice do on assignment 2? Well, to figure that out, it's going to be similar to this one. Again, pause these things between each one of these. Try to solve them for yourself, or go through the whole thing and then look through the answers afterwards. But in order to solve how they did on assignment 2, it's similar to what we did before, but instead of being assignment 1, we want assignment 2. Now, just changing the variable name obviously isn't going to work because the assignment 2 value is in the second element position. So what we're going to have to do is provide something for that placeholder for that first element. So we don't care what the assignment 1 vark is, so we can just underscore that and then comma. So that says unify this grades list with a list that has at least 2 elements. Put the second one into the variable A2, the first one into a don't care, and everything after the second one into a don't care as well. Okay, so just remove the second element there. And that gives A2 75. Good. All right, now how did student 1002 do on the test? So in this case, we don't have the name. We have student 1002. We don't have their name, so underscore. And grades is going to be similar. So there's 2 ways we could go about this. The simplest or the most naive approach would just be we don't care about the assignment, so 1, 2, 3 things there. The test, as we can see in the structure here, is the 4th element in that list, so we can just put a variable here for test. Close grades, close student, and done. Okay, so we provide don't cares to match all the elements here. We're assuming the grades list will always have exactly 4 elements, and the test will always be the 4th one. If that's something we can assume, then this is a query that will work. Okay, we can see that's the test grade for student 2, so it seems to have worked. A different approach would be to take this whole thing as a list, so let's call it L here, and then use a different query or a built-in function in order to do the rest of this work. So there's a built-in function called last, for example, that takes in a list, we'll call it L, and returns the value of the test here. So that will now take L to be all of the grades, and then last here just returns the last element of the list. Okay. So we'll take that as well. So some of these built-in functions can be useful as well at times, presuming I'm not asking you to solve them. I believe on the assignment, if not this year, then in previous years at least, I've asked you guys to create a last function yourselves. In that case, you obviously can't use the built-in last to do so. Okay. Did anyone get 100 on the test? So the test, again, is this last column. So we can ask a similar query here. So student. Now, we don't know who. Sorry, the query says who got 100 on the test. We don't know their name then, so we don't know their ID. We do want to know their name as an answer. So in the end, we'll say name. Let's just put in the variable name here. There's different ways, again, we could structure this. The query or the question here doesn't specify to take the last and the first name or the entire structure. In this case, this is going to return the list, last name, comma, first name, and somebody that got 100 on the test. So we've already seen how to check the test. So we can say grades L, and then ask the last thing in that grades list is the test, and then ask, does test equal 100? And we can use single equals or double equals here. It will actually mean the same thing because test is already bound to a value. Double equals just more explicit. We're asking a question, not stating a unification. So run this through. And just manually checking, we can see the answer should be Charlie Charleston, and that's the name we got. And we can see there's their grades, and the test is at 100. And we can backtrack to ask if anybody else did, and nobody else got 100. So there's our query here. Copy, paste. All right. Did anyone get 100 on anything? Now, this is a bit more of an involved query. So we want to start again asking for the name because we don't know who we're looking for. So we don't know the ID, and we'll use the same structure. Name is name. And again, if we don't want this list form, we can use a form like we did up here where we use square bracket last comma first. But it's a smaller part of the question to get the name here, so we'll just use the list. And let's focus on seeing how we can figure out if there's 100 anywhere in this list. All right, so we got the grades list. Let's call it L again for list. So now this queries every person and all of their grades. If I just run this query for now, we can see it's Alice and her grades, Bob and his grades, Charlie and his, Dave and his. So this doesn't answer the original question. It just says get everybody's name and grades. But with that information, we can then do more parsing to determine do any of these grades have the 100 in them. So what we're trying to see in this case, is there 100 here or in here or anywhere in that list? So we could do this with a very long or statement. You can put semicolons in a query to say or, but there's actually a built-in method for determining is an item in a list, and that's called the member predicate. So member asks, is a given key, so in this case we're looking for the key 100, in some list, in this case L. And that will return true for Alice because there's 100 here. And if we backtrack, it's true for Charlie because he got 100 on the test. And it's true for no one else. So the member predicate ends up being a very useful predicate every time we want a test list to have some sort of, not identity, to have membership, sorry, in some sort of test. Then this is how you do it. All right, did anyone get perfect on anything? What is each student's average grade? So we're going to assume equal weighting here, which means the average is just the sum of all four of these things divided by 4. So we're going to ask for any old student. We still want their name just so that we have the label to see who has what average. And then we're going to take the grades list. We could do this by taking the individual list and then unifying that with separate variables. But to do the addition, we need to have individual terms. So I'm actually just going to say A1, A2, A3, and test. So it says unify this list with these variables to any of these lists. So the first one will be this. So A1 will be 92, A2 75, A3 100, and test 85. So it's going to unify each individual variable with all the items in that list. And then all we need to do is a bit of arithmetic. So to do arithmetic, we say, let's say average is. So the keyword is means do the actual comparison or the actual evaluation. And then we just need to sum up all these values, A1 plus A2 plus A3 plus test, and then divide by the number of values, in this case 4. And there we go. Alice has an average of 88. Bob has an average of 63.25, 81, and 55, and 77. So it goes through each individual one, computing their average and reporting it. All right, that about does it for this introduction to Prolog Lists. And the next video we'll take a look at how we can use these lists in conjunction with all the stuff we learned about recursion in the previous videos in order to create some proper list processing predicates.